Good morning, students. So yesterday's class we just discussed about the data structures and the algorithm of two-pass assemblers. So we shall continue with the implementation by taking a program. That's also we started in the previous class. We shall continue with the same thing, and specifically we then move on to SIC, XC implementation. So that's what we're going to be doing it today. Fine. Yeah. So in the previous class, yeah, we have seen this opcode table, symbol table, as well as the location counters are the three data structures that is used for implementing the what do you call uh, implementing the assembler algorithm, right? So assembler takes two pass. The pass one is a definition pass, wherein addresses is allocated for all the instructions as well as the what do you call the declarations. So depending on the size of the declaration, the memory will be allocated. This allocation of the memory is done by using a integer variable location counter LOCCEN. And in the pass one, the addresses will be assigned. In pass two, the translations will happen. Wherein in pass two, we're going to convert all the mnemonics to operands and all operands to its addresses. Fine. Okay. This is what will be the case. Right. Okay. These two things means this is implemented in pass two of the algorithm. This much we have seen, and also we have taken an example program, right? And we started with how to assembling this. As I told, you will be given a program or a small code snippet, which you may need to convert it into what you call object. So this is in pass one. All the instructions will be allocated with the addresses specified in your start. So this is absolute assembly. But if it is not specified, if you are not specifying the address, the 0000 will be the address that is going to be used. And relatively, all other instructions will be incremented by 3 if it is a only SIC program, but the things will change in SIC. And based on the size of each of the variable, the size of the variable or constant, the addresses will be allocated based on that. If it is 1 byte, it is 1, and if it is 10 bytes or an integer variable of 10 locations, then 300 bytes will going to be allocated. Sorry, 30 bytes will going to be allocated. So this much we have seen. Yeah, we'll take up this program. Okay, this is a program which we consider, which will going to copy or read 10 bytes of data from your input device, and every time you're going to store it onto what you call your variable string one, right? So it is using indexed addressing mode also for storing, and it is testing the device as well as reading the device. Now we have some 10 instructions. 1, 2, 7 instructions, excluding all the declaration statements. So we shall assemble these. Remember, the assembler directives will not be converted into object code. The declarative statements will not be converted into object code. Assembler directives are just the guidelines to your assembler itself. The declarative statements will going to allocate the memory required as per the declaration. That's it. But the rest of the instructions, which all are there, they will be converted into the object code. So in our program, if you look at it, the instruction which is at row 2, 3, 4, 5, 6, 7, and 8. That means only the 7 instructions are there. One is LDX, one is TD, JEQ, RD, STCH, TIX, and JLT. Only these instructions will going to be converted into object code, and wherein this mnemonics will be converted into opcode, and the operands will be converted into what do you call the operands or the addresses, which is already been allocated in what do you call finding some disturbance. That's why I'm muting the participants. Fine. Okay, these 7 instructions will only be converted into object. How is it done? It will be done in pass 2. So we shall take each instruction. The first instruction here is our LDX 0. So LDX opcode will going to be 04. You can refer the opcode table 04 in hexadecimal. Okay, and zero's address is 1029. This is a simple direct addressing. So for that reason, the X bit is made equal to 0. You can make it out. There is no, it's not an index addressing mode, it's a direct addressing mode in SIC. So it is made equal, X is made equal to 0. And the opcode 04 is written in binary. You can see that zeros, first 4 zeros indicate 0, and the next 0100 indicates 4 bits. And in SIC instruction, we'll be having 8-bit opcode, 1 bit for X flag, and the rest 15 bits for the address. So we are supposed to represent 1029, that is the address of 0, which is a integer constant, to is represented by 1, is present at the location 1029. So it is written as 001 for 1, and 4 zeros for 0, and a 2 is written as 0010, and 9 is written as 1001. So this is the complete assembling of the first instruction. So resultant will going to be 041029, because if we take this 4 bits from the X, if you take 4 bits, that is 0001, then also you're going to get 1 only, right? But if it is an indexed addressing mode, X would have become 1. So I would have got 9, 1001. So instead of 041029, we would have got 049029. Getting the idea? That's how the means assembling will going to change based on whether it is an indexed mode or whether it is an direct mode. Okay, fine. Let's see the other instruction where the indexed mode is also there. Okay, then we have the next instruction, which is a TD. The TD's, what do you call, opcode is E0. And in device is a hexadecimal constant, which is having its declaration at the location pointer value or the address 1015, right? The same way here we are going to write. The E is written as 1110, that is your E, and followed by 4 zeros, that is your zeros. As it is not an indexed addressing mode, X bit is equal to 0, and we are writing 1 as 001, zeros by 4 zeros, and one more 1 by 0001, and 5 is 0101. So together all these things will make up your object code as E01015 hexa. Fine. So that last H is indicating that the opcode is in hexa. If you don't write also, it's not an issue. But so as to avoid the confusion, we are going to usually put an H at the end. Fine. So indicating that it is in hexa. But when we are writing it in a object code file format, we don't usually write this H. We'll directly write the values only. Fine. That can be done in that way. Fine. The next instruction is JEQ. The opcode of JEQ is 30, and in loop. In loop is the label where you are supposed to jump, and it is a backwards. You are going back. Fine. So in loop is at the location 1003, because we started all the instructions from we started assembling the program using the address 1000, right? That is 1000. So for that reason, the second instruction itself is in your TD. TD is having the label in loop. So the address is 1003. Fine. So how come the assembling happens? Have a look at this. So we are having 3 represented as 0011, and the 0 is represented by 4 zeros. X it is not indexed addressing mode, so X is 0. And rest of the thing, 1 is represented by 001, and zeros. 2 consecutive zeros are represented as 4 bits of zeros. And the last bit is, last one is 3. So that is represented by 0011. Sorry, 0011, right? Okay. The object code will going to be same as it is 30100 3 hexa. Fine. Assembling will going to be easier in the case of SIC. The reason remains is we have only two addressing modes. One is direct and another one is indexed. Apart from this, no addressing modes. But these things will going to be complicated as we move on to SIC XE, because their format 3 alone instruction is having 4 different types of addressing modes. That is immediate, PC relative, base relative, indirect. So the PC relative and base relative, all these things, and even others also, needs the computation of the target address, means the displacement and the target addresses and all those things. So that will complicate the issue. But it is a simple SIC assembler. This is only SIC. Fine. Next is read device in device, which is also a direct addressing. The opcode is D8, which is represented as D is 1101, and 8 is represented as 1000, and 1 and 0 and 1 and 5 is represented consecutively. As indexed addressing mode is not there, we are making X bit as 0. So the opcode means object code will going to be your D81015. So this is actually the role of your pass. It is going to convert the mnemonic to opcode, operand to address, which is very simple if the addressing mode is direct. But it is going to be a complicated task when the addressing mode is not a direct one, but instead if it is of a different category. We'll see that variations too. Yeah, next instruction, which is an index addressing mode. Please observe HTCH STR1, X. Now it is indicating that it's not a direct address, but it is index address, wherein we are supposed to use X bit as 1 in our instruction. So then what will happen, we shall see. So the opcode of HTCH is 54, so which is written as 0101, and 4 is written as 0100. That's for the opcode done. So sorry, I was supposed to make the X bit as 1 here, which is not being done. Yeah. 1 second. Yeah, this is supposed to be 1. Okay. Yeah, this is supposed to be 1. 54 is written in the binary representation. Now you can see 1 X bit is 1. Next is the operand address is 1016. So 001 is 4 zeros. 16, that's supposed to be 0001. 1 second. This is supposed to be 01. Okay. This is 1. There is 3001 zeros, 4 zeros, followed by 1, and followed by 6. 0110. Right. So opcode means object code. What we are going to get is, first one is 5 as it is we got. Next is 4 as it is we got. And instead of 1, we are getting 9, because X bit included 1001, which is going to make up to 9, right? And then followed by a 0, and then followed by a 1, and then followed by a 6. So the opcode will be 549016 hexa. If it was not indexed, I would have got 541016. As it is in index addressing mode, it is making up to 549016 hexa. That's what is the difference. Okay. Yeah. Next instruction is a TIX instruction. TIX opcode is a 2C, and the operand is count. Count address is 1026. Fine. Now let's see. Is a direct addressing. So simple assembling will happen. So 2 is 0010, and C is 1100, and X bit is 0 because it is not an index addressing mode. Then 1026 you are specified. Fine. And then this is the opcode, object code, what we are going to get, 2C1026. Right. So last instruction will going to be our JLT, wherein in loop we will going to jump. If it is less than, we'll go to in loop. DLT opcode is 38 and the address is 100. Right. Yeah. This is how it works. 3 represented as 0011. 8 is represented 1 followed by 3 zeros. X is 0 and 10003. This is what is being mentioned. So opcode will going to be 381003. Exactly. Right. So this way we have completed the assembling of or completed the pass to for assembler by converting all the mnemonics to opcodes and all the operands to its concerned addresses. Fine. Now have a look at this. This is what is the uh, result of the pass to. Right. We have location counter which was allocated in pass 1, labels and mnemonics and the operands which is our programs, and except first instruction till the 8th instruction we are having the opcodes for each one of them. So this is the task of assembling in SIC. So we shall see the variations with the different addressing modes. That's what we're going to be doing in the next part of it. But before that, we have some other concept. We have an object code file format. The object code after computation should be written in a specific file format. This is also an important task. Majority of the times they may ask you in the theoretical manner, what is the contents of a object code file format. So we shall see that now. Fine. Is written in 3 records. Every object code will have minimum 3 records. One more we're going to add up later, which we call it as reallocation record. So that's an additional one that will get added up later. After we shall see the SIC assembly. Right. Minimum 3 records must be there. First one is called as a header record. What this header record contains: the name of the program, starting address of the program, length. In these 3 information, the header record will going to be name of the program, starting address, and the length of the program. Yeah. The column, the records column. Record is something like a structure you can think of, wherein we're going to be having the number of data members in a structure. So each column represents, or each set of columns will going to represent a particular thing. Here in header record, column 1 is indicated by H, which indicates that the record is a header record. Right? It is starting from a H. Right. Column 2 to 7 will going to be the program. Whatever the name of the program you can give. So maximum from 2 to 7 in the sense you can give 6-character program name. Right. Column 8 to 13 will going to be the length of the program. Right. So again we're going to have 5 bits for specifying the length. I think that's enough for us. So maximum 4 bits we will use. Means addressing we will use. If the program is quite lengthier also, we will have a maximum of 5 bits. That's 2 to the power of 5 combinations is possible. Yeah. Next is text record. Text record, what it contains the object code in the hexadecimal format, but we don't put the H at the end of the each object code of each instruction, but it will be separated by comma. And remember, each of the records in all the 3 records, values are separated by comma. That's it, nothing else. The first column of the text record is indicated by T, which is telling that it is a text. Next, we're going to have 2 to 7, which is representing the starting address of the object code. And 8 to 9 will be the length of the object code in this record. Please remember this, length of the object code in this record. If you have program, in our program, we have 8 object codes. That's what means 8 instructions got converted into object, which may need only 1 record. That's enough. But if at all, if the program is quite bigger one, some hundreds of lines of code, then all the object code we cannot fit into a single text record. For that reason, we can use multiple text records. For that, if we are using multiple text records, in each text record, how much object code you are accommodating that is supposed to be stored. For that reason, in column 8 to 9, we're going to have the object code, the length of the object code in this particular. But we don't get such situation. We will not use such big programs. For that reason, one text record itself is quite enough. And 10 to 69 means to say somewhere around 59 records are available for you to fill up the object code. So maximum length will going to be 59 characters that you can accommodate within a text record, one text record, right? Next is the third type of record is called as end record. Header record, text record. The last one is end record, which specifies the end of the object code. And one more information it gives, the starting address of the first executable statement. Leaving all the assembler directives, leaving all the declarative statements, which is the first executable statements. In our program, if you look at it, LDX0 is going to be the first executable statement. So that will going to be the thing. And usually when we are writing the text record, the first text record will, first object code in the text record will going to be the first executable statements in majority of the cases. Right. The end record means end record column 1 is indicated by E, telling that it is end, and the starting address of the first executable instruction, that is in column 2 to 7. That's the three things, three records of what we have in our okay, the object code file form. Right. We shall see the example. We shall write the one of it. String. Our program is this. Right? Header record is H. Name of the program is string, and starting address is 1000. The size is 1029 hexa minus 1000, whatever the value, hexadecimal value we put again, that is going to be the size. Okay. Text record, we have this. Starting at T is a text record. Starting address is 1000. Starting address of the first object code is your 1000. And the rest 8 object codes we have written separating by comma. You can go back and have a look at this. We have here the 1, 2, 3, 4, 5, 6, 7. It's actually 7 object code we have, which is written separated by comma, and we are not fixing with H. Yeah, sorry. Okay. We are not fixing it with an hex. Okay. And the end record. End record is having the indication E, stating that it is an end. And 1000 is what is the starting address of the first executable statement. So this is the object code file format usually asked. See, let's discuss what and all are the possible things that could be asked. First thing, as I mentioned, the data structures used with 2 pass assemblers. That is 3 data structures. Location counter, symbol table, opcode table. Please remember, these are the only few things that is will be repeatedly asked, right? Repeatedly asked. Second one, you're going to be given a, second one is your algorithm for 2 pass assemblers. That is usually asked one is pass 1 of 2 pass assemblers. First is data structure. Second one is assembler of 2 pass assemblers. Means algorithm of 2 pass assemblers. Pass 1, which is a definition pass, right? And certain times they have asked the functionality of the assemblers and how it is implemented, right? That is the theoretical portion. And the next thing that could be asked is, you'll be given a program, small portion, right? They will give you the opcode also, don't need to worry. And looking at the starting address, you are supposed to assemble that. First is pass 1, where you allocate the addresses using the location counter based on whatever the address is been given. In the same sense, you are supposed to do the pass 2, that is convert the mnemonics to operand, mnemonics to opcode, and operands to its addresses. And the third thing that is going to be asked is the contents of object code file format. Majority of the times they have asked. Majority of the times they have asked. Or there is another combination that is possible is you have been given a code which you are going to assemble it by using 2 passes, right? After the at the end, you will going to get the object code at the end of the pass too. Something like this in our slides. What have we done? We have got the object code, and this object code is supposed to be written in this format as you have been mentioned in the example, right? So these are the only possible questions that will be asked, right? So if you have the clear understanding, you can do it easily, right? Nothing much to remember here except the stepwise implementation of pass one of the two passes. That's it. I hope you all have understood this, right? Okay, this about our SIC assembler. We have only completed SIC assembler, not the SIC XC assembler. That's what we shall look in the next part. Fine. One second, I'll share the screen. No issues. Okay. So the next part, what we're going to be seeing is majorly the machine dependent assembler features. There are few machine dependent assembler features. There are few machine dependent assembler features. And once we have completed this, we have completed the almost the module 1 with what you call assemblers. Then we need to go ahead and look at the loaders and linkers, right? So the major discussion here in this particular section will going to be machine dependent assembler features. Yeah. What is this machine dependent assembler features is SIC XC supports multiple addressing modes like PC relative, base relative, immediate, indirect, and all these things. How the assembler should function in this particular case is what is it. Based on the addressing mode, the assembler design will change. So we know that format 1 instruction, there is only opcode, there is no operands. So just the opcode, 8 bits, that's it, need to be mentioned, that's it. Format 2 is a register to register mode, wherein we're going to have 8-bit opcodes and 4 plus 4 bits for representing two registers, register 1 and register 2, right? Okay. So we shall see the example how the assembling will happen in this case. For example, have a look at this. And we shall see separate program, we shall take a separate program and we'll do all those things. But as of now, how the assembling happens with register to register, we shall see that. Okay. Add R is a register to register addressing mode, S comma T. This is what we are telling. Yes, you should add the contents of S with the contents of T. And the result is supposed to be stored in T, right? That's what is it. So add R, the opcode is 90. So S and T means registers are represented with the numbers of 4-bit numbers. 4 bits means we can represent 2 to the power of 4, that is 16 registers. But we don't have 16 registers in our what you call SIC in SIC XC. We hardly have 9 registers. But for that I cannot use 3 bits also because we have 9 registers. So as to represent 9 registers, so minimum we need to have 4 bits. We can represent maximum of what you call we can represent maximum of what you call 16 registers, but as we do have 9 registers, we are using 4 bits for each registers, right? So S and T is S register is number, accumulator is 0, X register, L register is 1, something like that. We have given the number at the beginning, right? The same numbers. So S register is 4 and T register is 5. Okay, you can see that here. Okay. These are the two registers, the 4 and 5 that is been mentioned. So the opcode is represented in 8 bits as usual, but this 8 bits will going to reduce as we go ahead with others, right? Okay. 1001 is for your 9 and zeros for your 0. and register 4 bits. 4 S is represented by 4, that is 0100, and 5 is represented by 0101, right? Next, one more example here. Mm, okay, COMPR is a compare register which compares the contents of two registers. X is compared with A. Now the opcode for COMPR is A0, right? And the X register is 1, A register is 0. So similarly, we have mentioned 1010 is your A, and 4 zeros is your zeros, and register 1 is represented 1 and 0 is represented as 0. This is how the format 2 instruction is been what you call assembled. We shall see the next set of addressing. So yeah, one more instruction, one more example we have is DIXR, which is BH. The B is represented as 100, 1011, and 8 is represented as 1 followed by 3 zeros. And R and S register, S register accumulator is one register here. So S register is 0001. Sorry, supposed to be 0000, right? Okay, because it's an accumulator. Accumulator is 0000. Fine, right? Okay, this is how the things is. Okay, accumulator is 0000, and our S register is 4. Right? This is how the first machine dependent assembler features we have seen. That is how to assemble with register addressing units. Next thing we're going to see is PC relative. It's time up. We shall see that in the next class. Okay. Thank you. Thank you for joining.